Lesson 314. Today's all about constructing the graphs of polar functions. And I'm going to tell you right now, and I'm not being facetious, this one's pretty cool. Okay, this one is going to be pretty cool. So we're going to see some different looking graphs that you haven't seen your calculator produce today. It's pretty neat stuff. Let's get started. First, there are two ways of going about this. I'm going to show you the way that I think is traditionally taught. To me, this is the hardest way to graph these, but this is the way it's traditionally taught. Since it's tradition, I do think there's some good things to tradition. I'll show you after this an example too, what I think is an easier way to actually graph these functions. So let's start here. It says an equation whose variables are polar coordinates is called a polar equation. So let's stop and review from last class. Polar coordinates. What were the two polar coordinates we had? R and theta. Okay, so if your equation has variables r and theta, that means it's a polar equation. The graph of a polar equation consists of all points whose polar coordinates satisfy the equation. So here's our polar graph that we saw last class. What we're going to do is sketch the graph of r equals 4 sine theta. So first, well, I'm going to fill in these values. We can use our hand trick to help us with these. But what these are unit circle values. So I want you to think through what we're going to do is take 4 times the sine. 4 times the sine, and we're going to fill in this table, and then we will graph it over here and look at what the graph looks like. So here, using our unit circle, which hand do you use, your left or right hand? You're using your left hand, and I'm giving you the pies. Which side's your pie side? Your palm of your hand or the back of your hand? Palm. So looking at the palm. 0, it refers to which finger? Pinky. Bend your pinky, flip your hand over. How many y's do you have there? 0. So it's going to be 4 times the square root of 0 over 2, which I'll go ahead and reduce. What's 4 times the square root of 0 over 2? 0. That's going to be our first point. So at 0, we have an r of 0. Let's go ahead and plot this dot right there. Plot a dot right there. Okay, next. At pi over 6. Go back to the palm of your hand. Which finger is your pi over 6 finger? The ring. Bend your ring finger, flip your hand over. How many y fingers do you have there? 1. Now, by formula, it's going to be 4 times that square root of 1 finger divided by 2, because cosine is always divided by 2. What does this reduce to become? 2. So at pi over 6, which we're going to say is right here, this is pi over 6, we have a value, r value of 2. So go to the second ring, plot that point right there. Okay, now continue on. Let's go to our next point. Pi over 4. Which finger is that? Middle. Bend your middle, flip your hand over. It'll be 4 times. How many y fingers do you have there? 2. Now you might notice, as we've said before, that sine and cosine, because they're periodic waves, they follow a pattern. What's happening to my square roots here? Increasing. Let's make sure everybody's understanding what the pattern is. They are increasing by how much? By 1 each time. So from here on out, we don't need to use the hand trick. We can just kind of simplify this quicker. This will be 2 square roots of 2. Now, that's a harder number to know exactly where that is, but that's going to be like it's going to be a little bit greater than 3. So here, this is pi over 4. This is pi over 4 here. I want you to go just past the third ring and put a dot. No, check that. This is just under 3. It's just smaller than 3. I'm sorry. Just smaller than 3. Put a dot right there at pi over 4. So now what I'm going to just start doing is I'm just going to follow the pattern. What square root should be this time? Square root of what? 3 over 2. So this will equal 2 square roots of 3. Now that's 2 times 1.73 approximately. So it's going to be like 3.4, just under 3.5. So at pi over 3, go to approximately 3.4. 1, 2, 3. Or 3.45, 3.46, something like that is where that point should be. Okay, let's come back over. At pi over 2, what's the sign at pi over 2?
It's going to be square root of 4 over 2.
That's right, which is 2. So that multiplying by 1, so this should reduce just to become 4. Okay, so at pi over 2, which is right here, we have that point. And I don't know if In case you don't know what these are, that's pi over 2, that was pi over 3, this was pi
I was
over.
wondering why you were plotting them like that. I was like, oh, he's just basing it off of the unit circle.
There you go. It's based off the unit circle. Okay, so picking back up. Now, what happens to the sine function after it reaches its maximum here? It starts counting back down. So we could fill these in quicker. It'd be 4 times the square root of 3 over 2, 4 times the square root of 2 over 2, 4 times the square root of 1. How am I getting these values? I'm just following the pattern. What happens after we go decrease to 0?
Negative.
You don't go back up yet. We keep decreasing till we get to negative square root of 4. So I'm going to keep filling these in. If you haven't yet, go ahead and fill them in yourself. Okay, now I'm at negative square root 4. What do I do once I get to negative square root 4?
Increase.
I start to increase. So now it's to negative square root 3, negative square root 2, and finally, negative square root 1. Okay, so as we reduce all of these, a lot of these values are familiar. So at 2 pi over 3, which is right here, 2 pi over 3, we should be at that 3.45 value right in there. At this point, at 3 pi over 4, we should be at 2 square roots of 2, which I said is just under 3, which is just under 3. That is 3 pi over 4. And then here, what was this value going to reduce to become? 2. And that is at 5 pi over 6.
It's like a mirror of the original.
Okay, what about this one? What are we going to get here? Four times, what's the square root of 0?
Oh, that's 0.
0. That's going to be 0 there. So we already had that point here, but that would now be, if this is 0 and this is 1 pi, we're back at a 0. So this graph so far, if you wanted to connect the dots, which we will in a second, at this stage, if you want to connect the dots, I'll go ahead and start now. What it should look like is this. Now, some of this doesn't look right because the lines here aren't actually spaced out correctly between pi over 3 and pi over 4. But it would go around like this. This is what the graph is looking like so far. Okay, I'm gonna pause there. Now, let's continue on with the values. Now, what do I get at 7 pi over 6? This is 7 pi over 6. Ooh, not 4, but that's 4 times negative 1/2, which is negative 2. So at 7 pi over 6, what do you do if you have a negative number?
Go down.
You go away from it. So it's actually this spot right there. So I double up and I hit this spot a second time. And then what do I get here? Well, I get negative 2 square roots of 2, and then negative 2 square roots 3. What's going to happen as you go around is you repeat all these values again. What I do is I repeat all these values. They get repeated as I go around. Now, how do they get repeated? Because all of these are negatives. And what does it mean if you have negatives? You go away from it. So all these values here, this is 5 pi over 4. That's 4 pi over 3. All these values are going away from it. And so they just repeat the values a second time. That's all that happens here. Negative 2 square root 3. Negative 2 square root 2. And finally, this would be negative 2. So what would we call this? Right here, it should be a circle. The problem is it doesn't look like a circle because, like I said, these angles aren't measured out right. This graph here, you see how these are evenly spaced? They shouldn't be evenly spaced. If you think in degrees, it's easier to realize this. That's 90 degrees there. Pi over 6 is equivalent to 30. This is 45. This is 60. There should be 15 degrees between these two, and 30 degrees between the axis and those pi's. So it's not spaced evenly. That's why it doesn't look like a perfect circle, but that's what that graph would be. Now, why do I say this today is going to be kind of cool? Is because you're going to see some graphs. Circle's not that cool to you. We're going to see some pretty cool graphs that you haven't seen before in mathematics. And now that right there took a long time. That was what I would call the traditional method of graphing. That's how the traditional method works. That's not the way I'm going to encourage you to do it. So starting in example 2, I'm going to show you, actually, we got to finish up this example. I'm going to show you a different way of doing so. Okay, so let's look at this one. So let's go through and fill out these values. Now, again, we're going to go pretty quick because it's going to be a pattern this time. -3 times with cosine at 0. What does cosine begin with at 0?
Oh, square root of 4 over 2.
That's right, because you're bending your pinky, flipping it over, you have square root of 4 over 2. If you think through the unit circle, that would be your value there. And then cosine counts down. So let's just go ahead and fill these all out all the way down. So -3, negative square root of 2 over 2, -3 times the square root of 1 over 2. Let's just go ahead and fill this chart out all the way down. So don't stop counting at 0. Continue to decrease until you get to what value? That's right, negative square root 4. Now you might notice this is kind of tedious doing it this way.
Yeah.
Pretty tedious. Where am I at? Negative square root 2 over 2. Almost there. Okay. And so we're going to plot all these points and see what we come up with. So here I have -3 times 1, which is -3. So at the angle 0, I need to be on the -3 circle. So what does that mean? Do I actually go towards the angle 0 from last class? Do we go towards it? No, we go the opposite way. So we go the opposite way, plot a point right there. That's the point right there, -3, 0. Because when you talk about points, you do the R first. That would be -3, 0 right there, that point. Okay, this one is -3 squared to, whoa, my goodness, that's not what I wanted to do. I want to take that away. That point does not reduce, so I'm going to just leave it like that. That will be that value. Now, where is that going to occur? This is pi over 6. That is -1.5 times approximately 1.7. I have no clue off the top of my head where that is.
Okay.
Sure. Type in -3 times square root of 3 over 2. -2.6. Okay, so at this, we need to go -2.6. So there's 2 point, I'm going to put it about right there approximately. The next one, I also don't know. These will reduce, so I'll keep those over. Okay, and next one, I don't know either. What do you get there? Did you type that one in the calculator yet?
Which one?
-3 times the square root of 2 over 2. Point 0.7. I'm gonna say -21 approximately. -2.1. -2.1. Okay.
Yeah, -2.
Okay, the next one will reduce. That's -3 times 1/2, which is going to be just simply -3 over 2. Whoops, -3 over 2, -3 over 2. So -1.5. That's this point right there. And that's pi over 3. Pi over 3. This is going to be pi over 2. At pi over 2, we're going to get the value of 0. So as I go around, what we're going to see is these values are going to mirror all the way around. This is going to be +3 over 2. So at 2 pi over 3, now at 2 pi over 3, we actually go towards it because it's positive now. So I would go to 1.5, 1.5, I'd place a dot, and you'll see that it's going to mirror all the way around. This is going to be positive 3 squared roots of 2, which is approximately, let me go back to the approximately 2.1, that value we had. So at 3 pi over 4 here, 3 pi over 4, we are approximately at 2.1 right there. This value is going to mirror that, but this time it's going to be approximately 2.6 positive because the two negatives cancel out. Goodness gracious, this eraser. Approximately 2.6. So here at 5 pi over 6, we would be at approximately 2.6, and the graph will just repeat as we go around. So I'm going to stop there for the sake of time. And if this was drawn to scale, whoops, if this was to scale, this should look like a circle as well. Now, unfortunately, this graph is just not very good. This would be a circle as well. Now, there's some rules for what makes something a circle with polar equations. And that's what your DOL is going to help you establish here. There are some rules. It says here this: if a polar equation can be written in this form, a sine theta or a cosine theta, where what does A represent? Look at our two examples, example A and example B. No, not sines and cosines. On example A, what was A represented by? 4. And what was A represented by on example B? -3. As long as A or the A value is a constant, then the graph will be a circle. Can you describe by rule the direction of the circle? That's going to be part A, and you can look at then part B and then C. Go ahead and try to fill these in. I'll give you a couple minutes to think about this. All right. Hopefully, after looking through those tables, you're able to fill out some of that information and make some observations. So now, here's what I would suggest you do for graphing. I think this is a much easier way of graphing a polar function. This is not the traditional way. The traditional way is by plotting points. I think it's slower, and I think it's a whole lot easier to mess up. Here's what I think is the better way of graphing these. And I think it's going to be good because it'll tie in stuff that you need to know anyways for the test. If we have to sketch the graph, let's say this is your task. What I'm suggesting to do, this is what I'll call my technique, is to first graph this function, change it from this is polar. This is polar. And think of it as a Cartesian graph, where I'll just write rectangular because it's in terms of y and x. So what did I do? I exchanged r with the letter y and theta with x. Okay, so let's think through this in rectangular. The constant is 2. That is the midline. Y'all remember that? That was when we learned how to graph these, this would be called the midline. So go up to 2, use your ID or something. Give yourself a midline to help graph this here. Now cosine, think of the unit circle. Does cosine, that's at +2, that's the midline, y equals 2. Does cosine start at its maximum, or does it start at 0? Maximum. So go up 2 units and put a dot. Now the points I'm going to graph, I'm just going to hit the major, I want to call it, how many lines did I put here? 1, 2, 3, 4, 5, 6. I don't like 6. Yeah, I do. Let's just call this 2 pi, which makes this 1 pi. In between here, this is going to be pi over 2. Now the values I'm really going to hit are going to be pi over 2, and then later 3 pi over 2. These are going to be like the major things of the unit circle. Like when I do a unit circle, those are going to be the major 4 values. So I'm going to put those on this graph. Okay, so cosine is what variable again?
X.
X. So cosine starts at its maximum. At pi over 2, what is cosine's value going to be?
Well, cosine values would be
0. So at pi over 2, we should have an x value of 0. Okay, so what does that mean for our graph? Come over here. It'll be at the midline. So put that at pi over 2. Okay, what happens when you get to pi?
That's close.
It's at its minimum, which is down Here's my amplitude down 2 units. So at pi, put a dot right there. Now what happens at 3 pi over 2 as this?
You go back to the zero, so you go back.
You go back to, we would call it a 0 if it was on the x-axis. We'd actually call it the, starts with the M, right? Rhymes with, there you go, you got it. You go back to the midline, put a dot. And then what's gonna happen when you go all the way around the circle to 2 pi?
Go back to the maximum.
You go back to the maximum. It's a full cycle. Now, why do I think this is an easier way to graph? Here's how you need to think on this on polar. This is what we call the pole. That is the origin. If you're on the midline, you're on the origin. When you are above or below, you're away from the origin that many units. So here's how I'm going to do this. This refers to 0 here. That's 0. This, if this is pi over 2, this is, should be here. This would be pi over 3. Yeah, it's pi over 3 because it's really close to pi over 2. Pi over 6 would be in this range. And this is the halfway point, by the way. So if you were to graph this wave, connect it, sine is always going to look like a wave. If you were going to connect this as a wave, oh, this isn't sine anyways, this is cosine. But cosine is also a wave. This is the that's the halfway point here. When you're at the halfway point for sine, if you think about it, sine, you need 1 finger to have a half. So you should be at the half. No. I'm wrong. You were right. That would be, to have sine, that would be a pi over 6. Yeah, that'd be a pi over 6. I'm sorry. I do it. Oh, this is cosine. No, I was right. Sorry. We're not doing cosine. I'm sorry. We're doing cosine. Sorry, to have 1 cosine finger. I'm going to the back of my hand. I want 1 cosine finger. What am I bending? To have 1 cosine finger. Looking at the back of your hand, you need to bend my index. What is the index? Pi over 3. So the halfway point is always a pi over 3. So that's 1 pi over 3. This is 2 pi over 3. This halfway point right here would be another pi over 3. What's the next pi over 3 to come? That's 2 pi over 3. That's 3 pi over 3. This is 4 pi over 3. This would be right here 5 pi over 3. And that would be the value of 3. Okay, so I'm going to plot these as I go around. So at 1 pi over 3, I should have a value of 3. Sorry. At 0, I should have a value at 4. So go to, at 0 is the angle 0. Go out to the 4th circle, put a dot. I'm going to erase this one for now. There's the dot. At pi over 3, we have the value 3. So go to pi over 3. Here's pi over 3. Go to the 3rd circle and put a dot right there. At pi over 2, what's the value?
2.
At pi over 2, we're going to be at 2. At 2 pi over 3, we have -1. So here's 2 pi over 3. I want you to think through this. What do you do if you have a -1? So I don't go to it. I go 1 circle away right there. At pi, I go to -2. So here's pi. What do I do at pi? I go 2 circles away. At 4 pi over 3.
I think 2 pi over 3 is starting from.
2 pi over 3 should be a -1. Oh, I missed one, didn't I? Good call. Right there. There we go. Where am I at 4 pi over 3? It says -1. Hold up. This is a -1. That's a value of, I should have put these on 1, 2, 3, and 4. Hang on. We need to start after pi over 2. Pi over 2 is 2. That's correct. At 2 pi over 3, we are at +1. Sorry. There we go. 2 pi over 3 is at +1. Where is pi at?
Pi is at 1.
No, pi is at
Over 0.
0. Pi is at 0. There we go. Starting to look at this going, this isn't right. At 4 pi over 3. Here's 4 pi over 3 down here. That's pi over 6, pi over 4. This is pi over 3. We're at +1. So you go towards it 1. Where are we at 3 pi over 2?
2 pi over We have two.
3 pi over 2, which is right here. You're at the value 2, which means 2 towards it. Where are we at 5 pi over 3? 5 pi over 3, we are at 3. This is going to be 5 pi over 3 right here. We're on the third circle. And then finally, skip to 2 pi, we are at 4, which is that point. Now we're going to connect our dots. Now, why do I do it this way? Because obviously I messed up. This is the right way to do it, the way you mess up. No, because this will hit the main points that you need to have. The others that we're going to be estimating on anyways, now get estimated when you just look at, you connect these dots. They just get estimated as, we were going to have to estimate them anyways. Now we don't spend all the time doing it on the table. This right here is what we call a cardioid. The name of this graph is a cardioid. It comes from a Greek word that means heart. Now, again, if you look at this, the problem is we're drawing it by hand. This would look like a heart if we drew it properly. What do I mean? It has that crack like a heart does. This is turned to the side. Why do you think this heart faces to the right?
Because it's a
Positive and cosine. What would be different if it were a positive and a sine?
It would be going up.
It would be going up. What if it were a negative and a cosine?
Go down.
Not down, negative cosine, it would be going to the left. And finally, what if it was a negative sine? It'll go down. What makes a cardioid is a cardioid has that crack, like you're thinking of with the heart. It has that crack where the two pieces meet together. Cardioid means heart in Greek. Where it comes from that Greek word. Okay, so let's try this again and maybe I won't mess up this time. How about this one? It says 1 minus 2 sine. So let's walk through this a little quicker this time. What's our midline? The midline is 1. So let's see if I can do this without messing up this time and show you how this is easier. Again, we established last class for 6 lines. That's going to be 2 pi. I'm going to put 1 pi here, which means pi over 2 is going to be there. And 3 pi over 2, the halfway point between pi and 2 pi, would be right here. That'll help us sketch this. Now, sine, does sine start at its maximum or does it start at the midline?
Yeah.
Midline. So put a dot at the midline. Because this is a negative 2 sine, it's going to go down first. Now, when should sine reach its maximum? If you think of a unit circle, when should it reach its maximum?
After putting it back to.
At pi over 2 is when sine should reach its maximum. But this one's getting multiplied by negative 2, which means it's going to get its minimum at pi over 2. So at its minimum, this is going to go down 2 points, 2 units. It's going to go down 2 units at pi over 2. Put that dot there. When should sine return back to its 0? At pi. Put that dot on. When should, now this one, it's going to be maximum since we went to minimum. When should it now reach its maximum, which normally would be its minimum? 3 pi over 2. So go up 2 units from 3 pi over 2. And then when would it return back to the 0? 2 pi. Okay, as we connect these dots, remember it's a wave. You can see that the halfway point is not at the pi over 3. If you just try to draw this wave connecting these dots. The halfway point is not at a pi over 3 this time. I should need to get that a little wider here. The halfway point should be a pi over 6. And you could confirm this with your hand trick. If you wanted sine to be a half, look at the back of your hand. If you wanted sine to be a half, which finger would you bend to get 1 for the numerator?
The middle finger.
Not the middle, that would give you 2 sines. You need to bend your ring finger to give you 1/2. So if you bend your ring finger, look back at it, what is that value? Your pinky, your ring finger is what? Pi over what?
Oh, pi over 6.
Pi over 6. So this point right here, which is halfway to the maximum, is a pi over 6. This is the next pi over 6. What's the next pi over 6 going to be? How many pi's over 6?
5 pi.
It's almost, that's it, because it's almost 1 whole pi. That's 5 pi over 6. This halfway point right here, sorry, right here.
wanna say, wait, like right before 3 pi/2?
No, it's just more than one whole pi.
7 pi/6.
That would be 7 pi over 6. This halfway point between the maximum and the minimum here
11
11
pi/6.
is 11 pi over 6. There you go. That's kind of how you figure out where those halfway points are. Okay, so this time, let's make sure we graph this properly. If it's negative, that means you go away from it, the point. If it's positive, you go towards the pole. So here, I have when I start at 0, I have a 1 here on the y-axis. So I go 1 towards 0. Put a dot right there. 1 towards 0. Now at pi over 6, we're going to use pi over 6 this time. At pi over 6, I have a value of 0. That means you're on the pole. The pole is like the origin. What about at pi over 2? Here's pi over 2. At pi over 2, it's -1. So do I go towards pi over 2? Away from it. So I got this point there. What about a 5 pi over 6? Which is over here. 5 pi over 6. Back to 0. What about at pi? 1. So 1 towards pi. What about 7 pi over 6? 2. Go ahead and add that in. You're at 2 at 7 pi over 6, so 2 circles towards it. What about here at 3 pi over 2? 3. Okay. Finally, 11 pi over 6. 2. So 11 pi over 6, we're at 2. And then at 2 pi, we would be back to 1. Okay, so what does that mean this graph looks like? What it looked like is this. We started here. It kind of looks like a diamond here, but it actually wraps in between. It's pretty cool looking. It goes like this. This graph goes here, and it wraps around like this. It hits that circle, it returns out, and it goes around like that and back. It's called a limacon, or limacon is actually how you say it. It has an inner loop. So limacon is how you say it. It's French. But what that word means is loop. This graph has a loop. It has an inner loop, and so they call it a limacon. If you call it a limacon, I don't blame you because we're in Texas, and that's how you would say that in Texas. But that's what they call it because that word means loop. It has a loop to it. Okay. So you see me graph a couple. I want you to observe some things about these equations. Oh, no, I got one more to do. Sorry. One more time. Let's make observations. Why did this one go down? A negative and a sign. Now, this one had an inner loop. You know why it had an inner loop? It has to do with these two numbers. But before I tell you the rule, I want you to look at these two. This one had a crack. And it had to do with these two numbers. If they're the same numbers, guess what you're going to have? A crack, which makes it a cardioid. If the numbers are different, it's a limacon. It won't always have an inner loop, though. And you're about to see that in the next one. On this one, is the sine number bigger or smaller? If the sine or cosine value, for whatever equation it is bigger, ignore the negative, that's telling you direction, is bigger than the constant, then you have an inner loop. If the sine or cosine is bigger, you have an inner loop. This one, what do you notice is different this time? It's bigger. We're going to see it doesn't actually have an inner loop. It's going to be a little different, but it's still going to be called a limacon. So a limacon is anytime the two numbers are not the same. So go ahead and put down here limacon. What makes it a limacon again? I'm sorry, equation-wise. What makes it a limacon?
When
When the numbers are different. Yep. Okay, so first, if we wanted to sketch this, the best way to do so, I think, is to look at the graph because you can do it faster than doing a table. So where's my midline on this equation? 3. So go up to 3. With your ID, draw a midline there. That's y equals 3. Now, does cosine typically start at its maximum or its minimum? Okay, so this one's negative, so where will we actually start instead? Minimum. So go down 2 units for the amplitude and put a dot. That's where we're gonna start. And remember, this is 2 pi. So that means this is 1 pi. Pi over 2 is gonna be in between. And we'll figure out the halfway, we'll figure out the other points here in a moment. This is gonna be 3 pi over 2. Those are the 4 that we hit on the unit circle, and then we'll figure out what are the halfway points in a moment. 0, 1, 2, 3, 4, and finally 5. Okay, so cosine. When does cosine usually hit its 0?
Usually after pi over 2.
No, not pi over 2. That's its pi. I said it wrong. Not at pi. That's its minimum at pi over 2. If you think through the unit circle, cosine hits its zeros at 2 spots. They hit at pi over 2 and 3 over pi over 2. I'm gonna go ahead and add those on there. At pi over 2 and 3 pi over 2, it hits its zeros. So cosine hits normally its maximum at 0 and its minimum at pi. But this time, since we have a negative, it's going to be opposite. It hits its minimum at 0, and so it's going to hit its maximum at pi. That's right. So go to pi, we'll be up at 5. Put that dot on there. After 2 pi, 1 whole period, this will return to be 1. All right, let's connect our graph. Let's connect our pieces, and then we'll figure out which pi is going between. So this is a wave, so try to draw it like a wave as best you can. Goodness gracious, I'm struggling today. Not that I'm ever that artistic, but okay, there's our wave. So this is cosine. So let's think about where it's going to be at the values 4 and 2 on the y-axis. So go to the back of your hand. You want to have 1 cosine finger because that would create a half. Which finger do you need to bend to have a half for cosine? Do I bend? I need 1 cosine finger. Which one do I bend to get 1 cosine finger? Pointer. Pin your pointer. Flip your hand over. What is that pointer? Pi over 3. That means these halfway points are at pi over 3. What do I mean by halfway? I mean halfway between the midline and the maximum. Those are going to be pi over 3s. So if that's 1 pi over 3, this one is...
5 pi over 3?
Nope, no, that's before 2 pi. Okay, now this one is just after 1 pi. So this one would be 4 pi over 3. And then finally, this halfway point.
5 pi over 3.
5 pi over 3. That's right. 5 pi over 3. So those are the points we're going to plot. We'll plot those points and we'll get our graph. So at 0, we need to go 1 circle towards it. Let me go ahead and just put those pi's in there. We're going to graph 0. Pi over 3 is up here. We'll do pi over 2. We'll do 2 pi over 3. We'll do pi. 4 pi over 3. 3 pi over 2. 5 pi over 3. And finally, 2 pi would be all the way around. Okay, so at 0, we go 1 unit towards it. Plot a point 1 unit towards 0. At pi over 3, we go 2 circles towards it, right there. At pi over 2, we go to the 3rd circle. At 2 pi over 3, go to the 4th circle. At pi,
You go to 5.
5th circle. At 4 pi over 3, 4th circle. 3 pi over 2 is 3. 5 pi over 3 is 2. And then 2 pi would be 1. So you'll notice this one, what it does is it's really flat in here. But out here, it really widens out. What they call this one is, sometimes they call it a dimpled limacon. Other times they'll call it a convex limacon. But either way, it's a limacon, but it does not have the inner loop. Now, what mathematically made it not have that inner loop?
The constant number being smaller.
The constant being greater than the absolute value of the A variable there. The amplitude of that wave. And so this would be called either, you could call it a convex or a dimpled limacon. I think dimpled would technically be correct if it's a 3 versus a 2. It goes off the ratio.
Will limacon still be correct?
I believe so. I definitely would not choose, cardioid is only when they're equal. Only. And it's a limacon
Let me do-
if they're different. It's just a, okay, so part D here. This time I'm gonna switch it up on you. I'm gonna show you the graph and let's see if we can figure out what type of graph it'll be. Okay, now you might be able to quickly look back through what we've done so far and have an idea. So looking at these pictures, what made this one a cardioid when you look at this graph? What do you notice about the minimum? Where's the minimum hit?
A 0.
0. That's what created the crack. Okay, this one had an inner loop. What made it have an inner loop? The negative. The minimum was a negative value. Okay, this one had neither a crack nor did it have an inner loop. Why?
Oh, because,
Because minimum
Did the minimum ever get to even 0?
No,
No. Okay, so when you look at this one, what would you guess you're going to call this one?
limacon.
You guessing it's a limacon? Why limacon?
because
It hits the sun negative minimum.
I agree with you. Its minimum is not the 0. So I'm going to guess it's a limacon. And you think it's going to have an inner loop or no inner loop?
no.
Yeah, inner
Oh,
loop.
yeah.
We'll find out. Okay, what equation is this? Is this a sine or cosine? Okay, rectangular or sinusoidal equation? The midline, what's the midline value here? 1. Is this a positive sign or a negative sign? Positive. What's the amplitude of this wave?
2.
There's your equation. That's what we're graphing. Okay, so let's plot these values. At 0, oh, they gave us the halfway points, which is helpful for us. This halfway point, it's a sine, will be at pi over 6. This one will be at the next pi over 6. What's the next pi over 6? It's the one's almost 1 whole pi. 5 pi over 6. Very good. The next one after that, 7 pi over 6 and 11 pi over 6. We're gonna graph those points. Okay, here at 0, we're gonna do the pi over 6. We're gonna graph pi over 2. I'm just mapping these out, what I'm actually gonna plot. 5 pi over 6, pi, 7 pi over 6, 3 pi over 2. I'm mapping out the ones that are good numbers for plotting purposes. And 11 pi over 6. Okay, plotting these around. Those are the spots that we're going to plot at. At 0, I need to go 1 towards it. So go 1 circle towards 0. At pi over 6, we go 2 units towards it. Plot that point. This point, what is that value at? It's in between here. Pi over 2. Sine gets its maximum, which is maximum is 3. So at pi over 2, we are at 3. 5 pi over 6. We go 2 towards it. At pi, we're at 1. At pi, we're at 1. Okay, now I'm getting into, I have a 0 at 7 pi over 6. So at 7 pi over 6, we hit the 0. So far, here's what the graph looks like. Let me switch colors. So far, it looks like this. If you were graphing by angle, it would go around. And so far, this comes around like that. It wraps back, and we are at this point right there. Now we are going to, that's at 7 pi over 6. That's where we stopped right now. That's where my angle is. What is this point right here? This is the minimum of sine. Where does the minimum of sine occur? This is 3 pi over 2. At 3 pi over 2, we have a -1. What do? Do I go down to down 1? No, you go away from it. So I now have this point there. Which means this graph, if you just follow the pattern, it goes up like that. And then at 11 pi over 6, guess where it returns?
0.
Returns to 0. So this thing would wrap around like that. And then it would continue on like this. So it's a limacon with an inner loop. By the way, an inner looped limacon is just called a limacon. No extra word with it. If it doesn't have a loop at all, that's where they would throw in the word dimpled or convex. Well, no, I'm not going to make any promises whether they're going to test on that or not. I don't think, I don't remember seeing it. I need to look back at that because I don't really remember, to be honest. But a limacon is if it doesn't have a crack and it's shaped like that. Okay, we have done a whole bunch. I want to see if you can fill these out from what I just said. I just gave you all the answers to this, talking through it. Let's see if you can write them in. All right. So now let's talk about symmetry. These graphs can have symmetry, and symmetry can be a little bit different. So first off, if you test this, I want you to think about what's happening here. I want you to think about this. When we talk about symmetry, someone's out. That's why. When we talk about symmetry, let's think about what's happening here. This is saying if your equation here could be exactly the same if you did this. Now, what is this actually saying? If you went this way, or if you started from pi and took away angles going this way. If you have perfect symmetry, you have symmetry with respect to what? As I draw this, if I draw it like this, what do my two arrows have symmetry with? What I'm doing here is I'm graphing this r theta. That means your radius with a theta going normal. And here going from pi, but going the opposite direction. What do I have symmetry? What do my arrows have symmetry with right here? Which axis? Symmetry with the y-axis. If we have symmetry with respect to the y-axis, which in polar is the line theta equals pi over 2. If you can test this and the equation works out the same, you have symmetry with the y-axis, which would be theta over 2. Verbally, what this means is it'll reflect on the y-axis. Now, if this is true, that means, what am I doing now? So this is kind of your picture. Let's call that for this one. Let's do the next one. What this is saying is if you took your normal graph and the normal graph that we start at 0 and go this direction, if we did this instead, this means you do a negative angle. If I go this way, what does this have symmetry with? This would be the x-axis. If you have a polar function, this is symmetric with respect to, they're going to call this one the pole. You could do theta equals 0. Now, actually, I'm going to do theta equals 0 because I think the next one I actually need to write pole. Sorry, theta equals 0. Okay, this would be x-axis. This is reflection. This is when it reflects on the x-axis. Finally, if this is true, here's what that means. Let me take this picture down and add it in. Here's what this last one's telling you. If you had your normal graph, and what's true is if you kept the angle the same, so I'm still going this way, but I get negative values now, which means you go away from it. So as you go along, my graph should be going this way. What am I reflecting on now? The origin. This is reflecting on the origin, which they will call the pole. The pole means the origin. This is reflect over the origin. That's the idea. By rule, some things are true. Quick test. R equals F sine theta is symmetric with respect to the, okay, I want you to just think, what is sine? What usually, sine is what letter? The y-axis. it's gonna be symmetric with respect to theta equals pi over 2. Sine will, a quick test will be symmetric with the line theta equals pi over 2. What about cosine? What would that be symmetric with?
0.
Theta equals 0, that's right. The x-axis. What this line is telling you here, if you do a test and it passes this test, which I'm about to show you how we do, then that means it is symmetric. If it fails the test, it doesn't mean it's not symmetric though. We're gonna see graphs that don't pass the test, but it's actually symmetric anyways. Okay, so that's what's kind of tricky about polars with symmetry. So now let's move into that. So this graph, this is gonna be kind of neat. We want to sketch the graph of 3 sine 5 theta. Okay, so based off the sine, what do you think it's gonna have symmetry with? Based off the fact that it says sine.
Pi over 2.
Y-axis. The y-axis, which is what in polar?
Pi over 2.
That's right. Y-axis, which is theta equals pi over 2. Now this graph, the inside letter here, it's called an n. What is our n on this problem? 5. Now note this down here. It says if n is odd, there will be n petals. So how many petals will I have? Is n an odd number or even number? Odd. So put 5 here for petals. If n is even, there will be 2 n petals. So what in the heck is this talking about? This graph right here is going to be what we call a rose. Okay, so Serenity, after desk, please. Sine usually gets its maximum where?
Sine usually gets its maximum
Pi
at
over
3 over
2.
2.
Pi over 2. Okay, this one though has its maximum is at pi over 2. Typically, the maximum is at pi over 2. So you would start, I'm going to jump down here to this first maximum at pi over 2. But this has a transformation. You see how it has a 5 theta in there? I need to say this is 5 theta equals pi over 2. Now, how would I solve for theta?
You divide by 5.
Divide by 5. So if I divide that by 5, what I'm going to get is theta equals, okay, this is pi being divided by 2 divided by 5.
Pi divided by 10.
Pi divided by 10. This gets its first maximum at pi over 10. Okay, so this is pi over 2. This right here is pi over 2. I want you to think about this. Pi over 10 is located where?
I want to say
That's half a pi. We need to be 0.1. That's 0.5. 1/5 of the way. I don't know. I'm going to put it about right here. I'm going to say this is approximately pi over 10, somewhere in there. We get its first maximum there. Now, what is its first maximum? 3. So we're going to be in the third circle. Whoops, at, goodness, that eraser, at pi over 10. So go out here to approximately where you think pi over 10 should be and put a dot.
Do we have to plot it?
Yeah, I'm going to show you how to plot it in a second. Now, the first minimum, when should sine have its minimum?
Pi over 2.
At 3 pi over 2. We should have a minimum at 3 pi over 2. So here's what we're going to do. We're going to take 5 theta and set that equal to 3 pi over 2. Let's do our algebra. How do I get theta by itself? Divide by 5,
3 pi over 2.
which is theta equals 3 pi divided by 10. Now remember, this is like 0.5 pi. This is 0.1 pi. So this would be like 0.2, 0.3 is somewhere in here. We're going to get the minimum, which is -3 comma 3 pi over 10. What do I do if I have a negative number here?
Go
Away.
Away. So I'm not going to go the third circle towards it. I'm going to go the third circle away from it. I'm going to just plot that about right here. Now here, I want you to think about this. There's a property for this that we haven't covered this year. But if I have a maximum that's positive and then a minimum that's negative, what do I have to hit in the middle of that? I'm gonna say it again. If I have a maximum that's positive number, and then I have a minimum that's a negative number, what has to come in between? 0. So here's how this graph is gonna look. You ready? It's gonna go like this. It's gonna come out here. It's gonna hit that maximum. It's gonna loop back. And then it's gonna come down here and hit that. And guess what it's gonna do?
Make 2 petals.
Loop back. Now, this was from 1 pi over 2, 1 pi over 10, I'm sorry, 1 pi over 10 to 3 pi over 10.
I use the negative.
Yeah. I get the negative three.
The amplitude, sorry. For sine, it goes to +3, then it goes down to -3. So I went to where I thought 3 pi over 10 is, and I just guessed 3 pi over 10 is about right here. Here's 3 pi over 10. Now, how am I getting this? Because pi over 2 is the same thing as 5 pi over 10. And so 3 pi over 10, if I said that's 1, I'm guessing 2 pi over 10 is somewhere in there. 3 pi over 10 is there. But what do I do if I have negative?
You go away from it.
I went away from it to down here. I went directly away from it as best I thought. Okay, so now I want you to think about this. The maximums and minimums repeat every, well, what is normally a pi for sine? I'm sorry, I said that wrong. What is normally a period for sine?
2 pi.
2 pi. It's usually repeats every 2 pi. But this time, because it's a 5 theta, they're going to repeat every, let's see, how do I get this isolated here? Divide by 5.
Would it repeat every 4 pi's over 10?
They're going to repeat every 2 pi over 5 or 4 pi over 10. So if my first maximum was at pi over 10, if I added 4 pi over 10, because that's what this is, that right there is the same thing as 4 pi over 10. What is 1 pi over 10 plus 4 pi over 10s? 5 pi over 10, which is right here. Our next maximum would be here. So this graph would look like this. It looped around this way. And then it looped around this way. And now it's going to come up through the 0. And it's going to hit this point. Whoops, missed. It would loop around and hit there and come back. How many petals is this supposed to have?
5.
5. We got 3. Okay, now comes the minimum. That was a maximum here. Now comes a minimum. We went from 1 pi over 10 to a minimum at 3 pi over 10 to a maximum at 5 pi over 10.
You go back to a minimum.
A minimum at what? 7 pi over 10. Let's say 7 pi over 10 is somewhere in here. 7 pi over 10 is going to have a minimum,
But it's negative. So
and it's going to be negative. It's going to be across. So we go away, and the minimum is going to be 3 units. So 1, 2, 3, somewhere in there, roughly. So I have that loop, and I have one more that I'm going to include on.
9 pi over 10?
It'll be 9 pi over 10. Will this technically be a maximum or a minimum? It went max, min, max, min, max. So over at 3, positive 3, you have a maximum. Whoops. A maximum here. And we get what we call a rose. Now, look at our rows. Did it have symmetry on the line pi over 2?
Yes.
Does it appear to have symmetry that way? Could you cut it in half on the y-axis?
Yeah.
Could you cut it in half on the x-axis?
No.
No. Notice it was sine, and that has to do with that. Could you cut it? Would it reflect over the pole,
Probably.
No.
the origin? I don't think so. I don't think this quadrant would go over this quadrant. So I think this would be the only symmetry it would have. Okay. So this is a rose. What makes it a rose, by the way? What in the equation made it a rose?
The inside of it.
The inside number there. If you have an inside number there, that makes it a rose. Okay, so on this one, go ahead just by equation. Is this a limacon? Is it a circle? Is it a rose? What is this? It's a rose. Let's go ahead and name it. This one's going to be a rose. That inner letter they call an N. What is our N on this one? 2. Now, go back to that note on the previous slide. If N is odd, there will be N petals. If N is even, there will be 2 N petals. There will be 4 petals. Good. The symmetry, because this is cosine. Cosine has symmetry with which axis?
So be- they
Whoops,
equals 0.
dyslexic. There we go, x-axis, which is theta equals 0, good. Okay, the first maximum, now on a unit circle, where should cosine have its first maximum?
At, pi,
Not at pi,
but,
it's a minimum.
should be at 0.
0, right? And 2 pi is all the way around, there's pi right there. We should have our first maximum at 0. Well, what do you have to do? You have to take your 2 theta, your argument, and say 2 theta equals 0. Now, how would I solve that?
Divide by 2.
Divide by 2. Well, this is easy math because guess what we still get?
Zero.
0. So theta equals 0. That means the maximum will be, what's our amplitude? 4 at 0. So at 0, we go to the fourth circle, put a dot. Now, let's talk about the first minimum. Where should the minimum occur at?
Pi.
At pi. But our argument here says 2 theta. So you say 2 theta equals pi. This is where the minimum should occur.
Pi over 2.
When you divide that by 2, we get theta equals pi over 2. And so the minimum is -4 comma pi over 2. So here's pi over 2.
You go away from the origin?
So
You
4
go away from pi over 2, so we go down 4 units. Now, this graph does not connect from here to here. You know how I know that? Because this is a maximum, it's positive. This is a minimum, and it's negative. If you go from a positive to a negative, guess what you have to do? You have to go through 0. So this graph is going to come through here. It's going to hit this point, and it's going to have to come back to 0 before it makes its way to there. Okay, that's where we're at right now. Now, maximums and minimums repeat every, now what should they repeat on? 2 pi. Well, it should repeat every 2 pi, but it's 2 theta. So what do I do to get rid of that 2?
divide by 2.
So maximums and minimums occur every
Pi.
pi. Now you'll see why it's 4, why we're going to get 4 petals mathematically. So if they occur every pi, if I had a first maximum at 0, where's my next maximum going to occur?
Pi.
At pi. So the maximum is 4, so I go 4 towards pi. So again, here's where we picked off from. We were coming back, that we hit 0. So I go to pi. I come around this way. And if I had a minimum at -pi over 2, where am I going to have my next minimum?
Positive.
No,
Positive
3 pi
4,
over 2.
3 pi over 2. At 3 pi over 2, we should have our next minimum, and our next minimum is at -4. So I go for that way.
So -4 3 pi over 2.
Yep. Whoops. Okay, let's talk about symmetry. Does this appear to have any other symmetry?
Yes.
Maybe the origin.
I think it has all.
It looks like it has all 3, doesn't it?
Yes.
It looks like it reflects perfectly across the origin. It looks like it reflects perfectly across the y-axis and the x-axis. So by appearance, we could do a test. We just don't have the time for it. By appearance, also, theta equals pi over 2. And the pole. The pole means the origin. So I'm going to put that in for symmetry as well. By rule, if it's a cosine, it should have it at 0. Oh, you know what? I didn't think about this. We could have on the previous one. This was a sine. You know where else? So sine normally has symmetry at pi over 2. You could find an extra one that was not on the list by saying 5 theta equals pi over 2. But this was going to be symmetric on pi over 10 as well. At pi over 10, if you drew a line, pi over 10, that would cut that flower in half as well.
Oh, yeah.
Because you take the pi over 2 and set that equal to 5 theta. We could have done that as well. Okay, so summary on a polar. It says polar equations can be written these 2 ways. Not polar, I'm sorry, summary on a rose. I want you to look at this graph and determine what you think the value of A is, and whether or not you think this is a sine graph or a cosine graph. So what's the A? What's the N? And then is it a sine or cosine function? How do you know? I'll let you think on that. All right, it says many polar graphs do not require a full 2 pi to complete one cycle. Use the polar equation and auxiliary graphs to determine if the domain restrictions for sketching one cycle. So on this graph, what I'm trying to say is this. Do I need a full 2 pi to get this graph, or does it double over itself? So on this one, the way to think through this is like this. You need to know if cosine's minimum and its maximum would be in the same point. So cosine, where does it receive its minimum and where does it receive its maximum? What two values on the unit circle?
0 and
This, I have one student who's following my way of thinking. For cosine, where is its minimum? Where is its maximum?
0 and pi.
0 and pi. Good. 0 and pi. We need to compare those two values. If I plugged in a 0, I'm at cosine's maximum, which is 1. So what's 3 plus 3? 6. What I need to know is when I get to pi, will I also be at the same point? Meaning, will its minimum be -6? So let's plug in a pi. Cosine of pi is what number?
Cosine of pi.
Yep.
Cosine of pi. Should just be 1.
So 3 plus 3 cosine 0. Whoops, I meant to put a 0. Equaled what number?
1.
Sorry, 6, because that was 1. 3 plus 3 is 6. Now you're going to do the minimum. What's 3 plus cosine of pi? Well, what's cosine of pi?
Cosine would just be square.
-1.
Yeah.
And so what's 3 times, or 3 plus 3 times -1?
-6.
Nope.
0.
3 times -1 is
Negative.
-3. What's 3 minus 3? 0. Okay, are those the same?
No.
Needs a full 2 pi. Now, how did I know that? Because these two did not equal each other. Let's try this one. Where does sine get its maximum?
And pi over 2.
At pi over 2. And where does it get its minimum? 3 pi over 2. I'm going to try those two values. For sine of 5 times. Hang on, I'm thinking through this if I'm doing this.